Namaste. This is JV and Dr. Vishal Saxena, professor in mathematics in the Faculty of Education and Methodology, JAYOTI VIDYAPEETH, Women's University, Jaipur. So today I am going to take a lecture on the topic Euler's method. This topic Euler's method this belongs to the course Numerical Computations under the program of BCA 6th semester of the university. So as already we know that in the numerical analysis, there are certain methods to solve the algebraic equations and the differential equations, partial order differential equations. So the Euler's method is one of the method to solve the differential equation or the ordinary differential equation. This method is a very basic and a very starting method to solve an ordinary equation uh, and ordinary differential equation with the boundary conditions. So after Euler's method, we can just apply the Euler's modified method also, and that will give the more accurate and more better value to the root of the equation. And but presently we are going to discuss the Euler's method, and when we just apply the other methods like Runge-Kutta method, Millen's predictor corrector method, or the Picard's method, other methods, then Euler's method is due to the easiness, it can be applied to find first the unknown value or the beginning value of the solution, and then the Runge-Kutta method or the other method can be applied to find the further values of to the root in the given equation. So initially we see what a Euler's method. In the Euler's method, again we are having a differential equation of first order. Look at this one. It is an ordinary differential equation dy by dx is equal to fxy. So dy by dx is equal to fxy, where y is the dependent variable of x and x is called the independent variable. And this derivative term dy by dx is equal to function fxy. Now, one boundary condition is given that along with this equation, that is y at x naught equal to y naught. So means the starting value of x is taken as x naught, and the corresponding value of y means the solution, and the corresponding value of y is taken as y naught, and it is corresponding value to the x naught. So, to make a general formula for the Euler's method, to make a general solution formula for the Euler's method, first we integrate this equation in both sides. So, we will get there like y1 is equal to y naught plus integration from x naught to x1 and function fxy dx. So, just we have integrated this equation with respect to variable x. And we will get as y1 equal to y naught plus x naught to x1 and in function f x comma y dx. Suppose that now we are taking our assumption. Suppose that fxy equal to fx naught comma y naught in the interval when x is greater than or equals to g x naught and less than or equals to x1. So it is our assumption that fxy is assumed as fx naught comma y naught in this interval between x naught and x1. Then this integral formula, this integration term will give us y1 is equal to or y1 is equivalent to y naught plus h into function f x naught comma y naught. So ultimately, this term is obtained from this equation, from this term there. And when we repeat the whole process in a similar way, means in general, then the n plus 1th value of y is given by yn plus 1 is equal to yn plus h into function f xn comma yn. So this is n plus 1th value of our solution of this equation. So yn plus 1 is given by yn plus h into function f xn comma yn for n is equal to 0, 1, 2, 3 and so on. In the Euler's modified method, along with same equation, this same equation yn plus 1 equal to yn plus h into function f xn comma yn, we will use one more equation in each and every step. That's why the root can be improved and ultimately Euler's modified method will give us a better solution as compared to Euler's method. But right now Euler's method is a very basic method and it is applicable in questions where the higher values are obtained and the initial values can be calculated by this Euler's method. So again, this method is having some importance. And now this Euler's method, how to apply this Euler's method for the problems? We see this one in this example. So the question is that use Euler's method or Euler's procedure to find y at 0 0.4. Y at 0 0.4 means for the value of x which is 0 0.4, we have to find the value of y. So y at 0 0.4 is required there for the differential equation dy by dx is equal to xy, and the boundary condition is given that y not equal to 1. And in this question, we are also given that h equal to 0 0.1. So one by one, we have to understand what or how to apply this method for this question. So first of all, we have to see what is our function fxy. The function fxy is always equal to the derivative term dy by dx. So therefore, here this function fxy is given by xy. Okay, so in the different problems, the function fxy may be different, but the procedure remains always same. So fxy is equal to xy here, and the initial conditions x not equal to 0 and y not equal to 1. X not equal to 0 and y not equal to 1. This can be just obtained by the given boundary condition. And in this question, one thing also given that h is already given here, h equal to 0 0.1. If h is not given in the question, then we can make ourselves the value of h, we can assume the value of h, but the one important thing is that always just we have to remember that the value of h should be very small. If h is very small, then the accuracy of the solution will be more and more. So definitely we have to take h as small as possible and to get the better solution. So right now h is already given 0 0.1. So in this question, because we are required to find y 0 0.4, so therefore in this question we have to use 4 steps and initial value x naught y naught is already given, and therefore one by one we have to apply this method and to reach at y 0 0.4. So first of all, look at here this one. This is the first equation. As you can see, this is the general formula of Euler's method. Yn plus 1 is equal to yn plus h into function f xn comma yn. So this is the Euler's formula. Yn plus 1 equal to yn plus h into function f xn comma yn. Next, first of all, we have to take n equal to 0. We have to put n equal to 0 in the first approximation, and we will get y1 as y naught plus h into function f x naught comma y naught. So just this formula, this equation reduces to this form for n equal to 0, and this is called the first approximation. Now put the values like you can see y naught is given that y naught is given that 1, we can see here, and h is already given 0 0.1. Function f is given in the form of xy, and x naught y naught, what is y naught, given 1, and x naught is given 0. So just putting the values in this equation, and after solving we will get this as y1 equals to 1. We should use scientific calculator to solve such kind of equations because ultimately the whole equation should be given in the single form, and so that an error should not be generated there, and therefore y1 is y1 is coming there 1 in the first approximation. For the second approximation, we have to put n equal to 1 in the second, in the first equation. Look at this first equation, and here n equal to 1 is just used to get the value of y2. So y2 is coming there y1 plus h into function f x1 comma y1, and now put all the values of x1 and y1 and function, and then just we will get this value as 1.01. So 1.01 is a value of y2, and this value is corresponding to value of x2. Is it? So this is y2 value which is corresponding to the value of x2 and which is 0.2. So ultimately we have just got the value of y2, and then we have to calculate for y3. So for y3 we have to use we have to put n equal to 2 in the first equation. Put n is equal to 2, and then in the equation number 1, and we will get the value of y3 as y2 plus h into function of x2 comma y2. So that one is y2 is already coming there. Y2 is already obtained 1.01. It is 1.01 and plus h into function f x2 comma y2. So h means 0.1, and then function f x2 comma y2. X2 means 0.2, and then y2 1.01, and solve this term to get the value y3. So y3 is the value of y, is the value of y, means value of solution, and it is corresponding to the value of x3. And finally, because we have to find y4, y4 is just corresponding to x4 value, and x4 is 0.4. That is the question. At 0.4, we have to find the solution, means y. So finally, put n equal to 3 in this first equation, and then we will get its value as y4. Y4 is coming there y3 plus h into function f x3 comma y3, and now put the value of y3, x3, and the value of h and the function's value. So just on putting and on solving this term, we will get the value of y4, and that is coming there 11.06 1106. So this is the value of y. What is meaning of y? Y means the solution. That is the solution for our given differential equation, and that is corresponding to the value of x4. So in this way, the Euler's method can be applied to solve the equations, and but Euler's method is not giving so accurate solution as the Euler's modified method or the other different methods. But it is still useful because it will give the solution, and when the question is very question demands the solution for the high values. So in the beginning, the Euler's method can be applied to get the initial values. So this is a Euler's method, and it is applicable for the differential equations in numerical analysis. Numerical analysis, one important thing just consists of the accuracy. So whenever just we will use the scientific calculators or other mode, we should write our the whole term, whole equation in a single way, so that the accuracy the error should not be generated there, and the answer should become the correct one. So this is the method of our Euler's method, and in the next method, in the next lecture, we will discuss about the Euler's modified method and the other methods in this part of numerical analysis for the differential equation. And with this, I am concluding today's lecture. Thank you.